In today's video, we're going to study a new coordinate system, the polar coordinate system. Right now, all of the work that we've been doing up to this point has been in the rectangular coordinate system. Also known as the Cartesian system. Right? In this system, we have a set of axes, x and y, right? And any point, x comma y, can be represented as, any point can be represented as the ordered pair x comma y, right? Where x measures the distance the point is from the y-axis, and y measures the distance the point is from the x-axis. However, there's going to be times where our work is going to be easier to do in a different coordinate system. So the polar coordinate system. Again, we have our axes. Now our point is represented by an ordered pair r theta. R measures the distance the point is from the origin, and theta is the angle that that segment makes with respect to the positive x-axis. So let me write that out. R right? So again, r is the distance from the origin to the point. Theta is the angle that the segment OP makes with respect to the positive x-axis. Now, given a point P, we wish to be able to convert it from polar to rectangular or rectangular to polar. Right? Well, what we're going to do is notice that this figure, right, the line segment OP is a hypotenuse. So if we resketch that, I'll do it this way. There's our point P. That is distance r. Notice that we can do this. There's our distance y. And there's a distance x. Right now, from right triangle trigonometry, cosine of theta was adjacent over hypotenuse, right? So in this case, it will be x over r. Sine of theta was opposite over hypotenuse, so y over r. Solving for x and y, respectively, we get x is r times cosine of theta. Y is r times sine of theta. Now, since r is hypotenuse, we can use Pythagorean theorem to write r squared is x squared plus y squared. Also, we know that tangent of theta is opposite over adjacent, so y over x. However, recall that the range of the inverse tangent function is minus pi over 2 to pi over 2, right? Open. However, it is conventional to take theta to be between 0 and 2 pi. With this convention, we find that we get several possibilities for theta. We can have 2 pi plus the inverse tangent of y over x if x is larger than 0 and y is less than 0. In other words, if our point lies in the fourth quadrant. It'll simply be the inverse tangent of y over x. If x is greater than 0 and y is greater than 0. In other words, if we're in the first quadrant. We get pi plus the inverse tangent of x whenever x is less than 0. In other words, if we're in the the second or third quadrants. We get pi over 2 for x being 0 and y being larger than 0. And we get 3 pi over 2 if x is 0 and y is less than 0. And up here, these really should have been greater than or equal to's. This is all going to be summarized in this table. So if we want to go from polar to rectangular, we have x is equal to r cosine of theta and y is equal to r sine of theta. If we want to go from rectangular to polar, then what we have is the relation r squared equals x squared plus y squared, and tangent of theta is equal to y over x. Well, let's take a look at the point 0, 3. We want to explain this in polar coordinates. Okay? So what we do is take, r squared, x squared plus y squared. We get r squared to be 9, which means that r itself would be 3. We also have tangent of theta is y over x, so 3 over 0. That's a problem, that's undefined. Well, since y is positive, this means that theta is pi over 2. Oops. So the point in polar coordinates, r theta, is 3 pi over 2. Well, now let's take a look at the point. 5 root 3 negative 5, and convert this into polar. Again, what we're going to have is r squared, right, is x squared plus y squared. So we're going to have 25 times 3, which is 75, plus 25, which is 100. This, of course, means that r is 10. Tangent of theta, y over x, so negative 1 over root 3. Now we look at this and we go, okay, this is fourth quadrant. So to get a proper angle, we have to go 2 pi plus inverse tangent of negative 1 over root 3. Inverse tangent of negative 1 over root 3 is negative pi over 6. And so we get theta to be 11 pi over 6. So our polar point would be 10, and then 11 pi over 6. Okay. Look at the polar point, 3 pi over 3. To describe this in rectangular, we use x is r cosine theta. Right, so that's 3 times a half, which is just 3 halves. And we have y is 3 sine, r sine of theta, right? So 3 sine pi over 3. Sine of pi over 3, root 3 over 2. So in rectangular, our point is 3 halves, then 3 root 3 over 2. Now consider the point 2, 3 pi over 2. X will be 2 times the cosine of 3 pi over 2, which is just 0. Y, 2 times the sine of 3 pi over 2, which is 2 times negative 1, so negative 2. Thus, our point rectangular, right, is 0, negative 2. Now consider the polar point 6, negative 5 pi over 6. So x is 6 times the cosine negative 5 pi over 6. Right, so that is negative root 3 over 2. So we get negative 3 root 3. Y will be 6 times the sine of negative 5 pi over 6. Sine is negative a half, so we get negative 3. Right? So in rectangular, negative 3 root 3, comma negative 3. Well, just like we have curves in the coordinate plane, right, rectangular coordinates, we can have curves in polar coordinates. So a curve in polar coordinates is called a polar curve. Right, this can be described by an equation in r and theta, which is called a polar equation. Unlike in rectangular, right? So in rectangular coordinates, we have the two axes like this, x and y. So in polar coordinates, we don't really have axes, right? So we'll have lines like these, so on and so forth, to represent the angle theta. Right, and then we have little discs. Right, and the discs would represent the r coordinate. So let's take a look at the polar equation given by r equals 2a times cosine of theta. Right, for a larger than 0. We want to represent this in rectangular form. So start with what we have. Well, we know that r, right, is square root of x squared plus y squared. That's going to equal 2 times a. Cosine of theta. Well, we know x is r times cosine of theta, right? That would mean that cosine of theta is x over r. But r was the square root of x squared plus y squared. So we get that cosine of theta is x over the square root of x squared plus y squared. If we multiply through by that square root of x squared plus y squared, what we get is x squared plus y squared is now equal to 2ax. X squared minus 2ax plus y squared is now 0. All I'm doing here is grouping. If we go ahead and complete the square, we get x minus a squared plus y squared is equal to a squared. Well, notice that this is a circle of radius a and centered around the point A0. Consider the polar curve r equals some function of theta. We're going to have parameterization c of theta, right? X of theta comma y of theta, which is r times cosine of theta, r times sine of theta, but r is f of theta, so we get f of theta times cosine of theta, f of theta times sine of theta. So the slope, right, remember, right, that the slope of this parameterized curve is given by dy dx, which was y dot over x dot. So for our polar curve, right, we're going to have dy d theta over dx d theta. But y was f of theta times sine of theta. So f prime of theta times sine of theta plus f of theta times cosine of theta all over f prime of theta times cosine of theta minus f of theta times sine of theta. So this formula right here gives us slope of a polar curve. In other words, it gives us dy dx for a curve that is described by a polar equation r equals f of theta. What this says then is the tangent line to a polar curve r equals f of theta at some point theta equals theta naught is y equals f of theta naught sine of theta naught plus f prime of theta naught sine theta naught plus f of theta naught cosine of theta naught over f prime theta naught cosine theta naught minus f theta naught sine theta naught all times x minus f of theta naught cosine theta naught. if f of theta is larger than 0, then the polar region that's bounded by r equals f of theta and the rays theta equals alpha and theta equals beta is a sector. Divide this sector into n narrow sectors of equal angle, delta theta equals beta minus alpha all over n, where we're assuming, right, that alpha is less than beta. And this is, of course, corresponding to a partition. Alpha equals theta naught, which is less than theta 1, which is less than theta 2, so on and so forth, which is less than theta n, which is beta. We'll recall that the area of a circular sector of radius r and angle theta, measured in radians, of course, is given by 1/2 r squared theta. If our delta theta is small enough, then each narrow sector is nearly circular. Which implies that the j'th sector is a nearly circular sector of radius f of theta j and angle delta theta, which implies that the area of this sector is about 1/2 f of theta j squared times delta theta, which means that the total area of our sector is approximated by the sum j equals 1 to n of 1/2 f of theta j squared times delta theta. Now, as n approaches infinity, right, this is going to get more accurate. So what we find is the following. If f is a continuous function, then the area bounded by r equals f of theta, theta equals alpha, and theta equals beta, with alpha less than beta, is 1/2 the integral from alpha to beta of f of theta squared d theta. So we wish to find the area of one petal of the rows r equals 3 sine of 2 theta. So let's go ahead and take a look. So we're going to come over to Wolfram Alpha, we're going to do polar plot. And then 3 times sine of 2 times theta. And theta will go from 0. Let's just do 2 pi. Well, let's just do pi. That's 1 full revolution. Let's see what this gives. Oh, I'm going to have to do 0 to 2 pi. Okay. So we want the area in just one petal. Let's do yellow. So it's not going to matter which petal we choose, right? Because all the petals are going to have equal area. So let's just find the area of this petal. Now to determine the angles, right? Notice that the petal starts and ends at the origin. That means the radial component is 0. So we go 3 sine of 2 theta equal to 0. And then solve. Right, this means that sine of 2 theta has to be 0. And that means that 2 theta would have to be need more room. Has to be in one of 2 sets. So either the set I don't like the way that this is coming out. I'm going to do it this way. Two theta has to either be 2m pi I don't know why I did it this way. Two theta would just have to be 2m pi. That's why I did it. Okay. For m being an integer, or 2n or 2n plus 1 times pi for n being an integer, right? So what I could have done is said that 2 theta has to be m times pi, right, for some integer m. Right, because sine is 0 only at multiples of pi. Well, this would mean that theta would have to be in the set of all values let's call them theta prime, such that theta prime is equal to m over 2 pi for m being an integer. So what we're going to do is take theta to be between 0 and pi over 2. So the area will be 1/2 integral from 0 to pi over 2. 3 sine of 2 theta squared d theta. All right. Well, this is 9/2 the integral sine squared, which is 9/4 the integral 1 plus cosine of 2 theta. These should be 2's. I'm sorry. There should be a 2 theta in here. Which makes this a cosine of 4 theta d theta. Well, if you notice, cosine is 2 pi periodic. So cosine of 4 pi would be pi over 2 periodic. We're integrating over 1 full period of cosine of 4 theta, which is going to make that automatically integrate out to 0. And so we're going to be left with 9/4 times pi over 2 or just 9 pi over 8. So you should recall that the length of a curve of the form c of theta equals, not c of theta, c of t equals x of t, y of t, was s equals the integral from a to b square root of x prime of t squared. So I'm going to use the notation x dot squared plus y dot squared. Well, the square root of x prime of theta squared plus y prime of theta squared. So f prime of theta times cosine minus f of theta times sine squared plus, and then f prime of theta sine plus f of theta cosine all squared. It'll be left to the viewer to verify this algebra, but we'll be left with f of theta squared plus f prime of theta squared. Which leads to this result. Right? We're going to look at the curve 1 plus 4 cosine of theta and determine its arc length. So first what we need to do is determine intervals. So what we're going to have to do is look at the graph. Right, so let's go ahead and do that. So polar plot 1 minus 4 cosine of theta. And let's just see what this is going to give without specifying a domain. I put minus instead of plus. That should have been a plus. Let's try that again. And we see it goes from 0 to 2 pi. Right, so this curve has a specific name. I'm probably going to mispronounce it, but this is known as a limicon. That should be a comma under there, like that, right? Yeah. So what we're going to have is length is the integral from 0 to 2 pi square root 1 plus 4 cosine of theta squared plus now its derivative, which is negative 4 sine of theta squared d theta. One plus 8 cosine of theta plus 16 cosine squared plus 16 sine squared. Okay. Well, 16 cosine squared plus 16 sine squared is 16. So you get the square root of 17 plus 8 cosine of theta. Now that cannot be done analytically. So we're going to come back over to our CAS to evaluate it. I see what I did. Close that out. So we get about 25.527.